Hello everybody. This is the first and only topic or video on curve sketching. And the whole idea behind curve sketching is really we're going to have curves and we're going to try, like this is a curve, and we're going to try and make sense of the important points on the curve. In fact, there's really only a couple different points that we need to care about. We have this point and this point and this point. Those are important. They're called x-intercepts, which I'm sure you've heard of before. And that'll be related to the original function f of x. You'll also have things called maximum and minimum points. This would be a maximum, this would be a minimum. High and low points. They are called our critical points. They just have a special name called critical points. We'll see they're related to the first derivative. And then we're going to have something really special, which kind of happens at the middle of the function here, which is called an inflection point. And that's where the curve turns from a sad face shape to a happy face shape. So you can see the function kind of gets twisted there and the story changes a little bit. But these are the three big ideas we're going to cover today. Inflection points. Those inflection points are related to the second derivative. Okie doke, so let's get started. Some of this stuff I'm going to be skipping through very fast because it's not as important as the other stuff. So curve sketching. It says we can use our knowledge of limits and derivatives, especially derivatives, to help us sketch the graph, or at least understand what a graph looks like. And the most important pieces are, like I've written here, intercepts, critical points, and then the increasing and decreasing sections, which are also called the concavity, which we'll get to later. But let's just fill in a few of the gaps. If we look at this function here, which this is the function given, it has a vertical asymptote at x equals 3. So what I'll write, the asymptote is vertical, it's where the function never touches. There's a vertical asymptote at x equals 3. So just the basic understanding of the curve, that's a point that the function can never touch, it just tries to. And the reason we have that, you might remember, is on the bottom here. If we set this equal to 0, it's a point where we would divide by 0. So what number makes the bottom 0? It's 3. We would divide by 3 minus 3, which is 0. We would be dividing by 0. So in other words, that's why there's a vertical asymptote at 3. It's because of that rule. On another note, there's what's called a horizontal asymptote. At y equals 2, which you can see this line here is y equals 2. It's another line that it goes on forever and never touches. And I'll talk about that more in a second. But just so you know, if there's a vertical dotted line that it doesn't touch, it's an asymptote, vertical asymptote. We covered it in unit 3, I guess it was. And then you can have horizontal ones as well. Hey, Ibrahim, I never saw you come in. And Muhammad, or Ali. Intercepts. Let's talk about some intercepts. What does it mean to have an intercept? Well, they're also called roots, zeros, and solutions, but I'm going to be calling them intercepts. And they're the values of x that satisfy f of x equals 0. Or in other words, if you had an axis like this, where is the function y equals 0? Well, these points could be where y equals 0. So we'll notice that if we set y equal to 0, you can solve for these. So I'll make a note. If you want intercepts, x-intercepts, you set y equal to 0, and then you solve for x. You've probably seen that before. If you want y-intercepts are where it crosses the y-axis, so maybe those two are y-intercepts. You would have points where x equals 0. And if you wanted to solve for that, you would set your x value to 0, because that's what it is. And then what do you think you solve for? Well, it's a y-intercept, so you solve for y. Let's do that. Find the x and y-intercepts of this function down here. X and y-intercepts of this function. So first things first, if you want the x-intercepts, you set y equal to 0. Let's do that. 0 equals x cubed minus x squared minus 6x. Let's solve that. What do we have to do to solve it? Well, we take out the common factors first. So any common factors in this? I can see an x. Take the x outside. You end up with this. Same thing as we saw last unit, you can factor this and figure out what the numbers are. This is the last time I'll do this, so I might as well do it. What two numbers multiply to make -6? Make -1. So we can either have this combination, or we can have this combination. And there's only one combination there that will give us the answer that we want. We need, what, a -6? You need to add them together to get a -1. It's going to be this one here. -6 and 1. Nope, -6 plus 1 would be -5. And we need a -1, Ali. So be careful there. We want 2 and 3, yeah? 2 and -3. How do we solve that for x? Well, honestly, it's very simple. Take each factor, now that it's split up, set them all equal to 0. So easy. This one, x equals 0. That's our first x-intercept. The middle one, x plus 2 equals 0, set it to 0. That means x is -2. That's our next intercept. Our third piece, x minus 3 equals 0. Set that to 0, solve that for x. It gives us this. Okay, so what we have is 3 x values. If I was to write a table of values, because I'm going to be doing this a lot today, if I was to set those into a table of values, what it means is that when x is 0, or x is -2, or x is 3, remember they are x-intercepts. That's where y is 0. So it gives us 0, 0, and 0. Those are all the values where y is equal to 0. If I was to make this on a number line or a graph, you would have at -2 and 0 and 3. Your function would cross there. So maybe the function looks like something like this, right? It would go through at those points. I don't know if that's what it looks like yet, but that would be the idea. Okay, those are our x-intercepts. Let's solve for our y-intercepts. Sir, do we write the whole coordinates? You should, and the whole coordinates would be this, okay? So you would have to write you would want to write those out to be very clear. So you could write 0, 0, -2 and 0, 3 and 0. Maybe I would suggest doing this. Okay, all you need to do is take the x value, put it into our function, and get back the y value. You always go back to the original function for that. Clear so far? If you have any other questions, let me know. Y-intercepts, which again, this is review, hopefully from high school. You set x equals 0. This is a really easy one. You're solving for a y. This is 0 cubed minus 0 squared minus 6 times 0. Well, that thankfully or easily is y equals 0. So all we need to do is say that that's our y-intercept. We already had that in our table, you'll notice, hopefully. This y equals 0 is this, which gave us this. So our intercepts are hopefully clear. All right. Maybe I could write it more clearly. So our intercepts are this. So I know I'm kind of cheating here. But this would be kind of our final answer. And you would be perfectly fine writing either of these. The table of values is clear. The coordinates themselves are clear. That's the big idea. And if you wanted to make a sketch, because we can now make a sketch, which is not necessary. Sorry, my writing's not very good today. You could do this. All right, I've got my -2, my 0, and my 3, and it would look like this because it's a cubic, and that's what cubics look like. If you don't want to make the sketch, you don't need to make the sketch. I'm just making it there so you can see it. We'll be making much more interesting sketches later. Okay, so that's a review. I wanted to cover that because, not just because of the idea of intercepts, where it crosses the x or the y-axis. I wanted to show you the method for solving for x, where we split this stuff up. If you understand that, you'll do very good today. So let me know if there's any questions. Otherwise, I'm going to go quickly. So vertical asymptotes, what I mentioned before, is a line in the graph that you want to get to but never quite get to. So sometimes it looks like this. You might have, we saw this with limits. The function tries to get to it, but it never quite reaches it. How do we find it? The vertical asymptotes can be found by finding x values that make the denominator 0 and they can't be canceled. If they can be canceled, they're holes in the graph. Let me show you what I mean. Just very quickly, let's just factor this and see if anything cancels. The graph, factor the top, just like with limits. We have, if you work that out, it's a 4 and a 3. Let me just, as a reminder, or maybe this is the first time you've seen this, I don't know. Yeah, some students are not very good at factoring. It happens. So, oops, your calculator can factor it. You probably already know this, but go mode 5, and then you want to solve a quadratic form, so it's the third form. So just put in your a, b, and c. A is 1, b is the number in front of the x, which is -1, and then your next number, c, is going to be -12. Okay, in quadratic form, a, b, c. Press enter, that'll enter the 12. Press enter again, it'll give you your first root. It says 4. Of course, that's x equals 4, which means that x minus 4 is 0. So you want to take the opposite. Whatever it gives you, if it's 4, take -4. In this case, it's 4 and -3, so it's the opposites, -4. That's a lot longer process than doing it by hand. But if you're having trouble, especially with more complicated ones, that's what you should do. So what do I notice here? If these factors cancel, it means there's a hole at x equals -3. So we can say there's no vertical asymptote. Which is why when we look at this graph, you can see there's a hole when x equals -3. I'm not going to talk about that anymore because we actually saw that in limits. It's just a little review. Really the only thing you needed to mention or needed to think about in the beginning is try factoring first. Let's see an example where we actually have a vertical asymptote. So this graph looks like this. And we can see even before we look at it, or sorry, even before we do the question, that there's a vertical asymptote at x equals 2. But let's see if we can figure out why. Well, take our function. We want to factor it. We can say 1 over x minus 2 squared. Well, can that be canceled? Or I'll say, in this case, if we're asking for vertical asymptotes, how do you find it? You set the denominator to 0. So take the bottom, set it to 0. Take this denominator, set it to 0. So x minus 2 all squared equals 0. That's easy to solve. Try to get the square root to cancel the 2. Of course, square root of 0 stays the way it is. So really all we have is x minus 2 equals 0. And if you solve that, x is 2. And so it confirms what I said. You can say there's a vertical asymptote when x equals 2. And that's really all I'm going to say about that. It's mostly review. I don't know if you'll get a question on that anywhere else in the course. I just wanted to mention it. So in case it comes up anywhere, you know how to handle it. Long story short, if you want a vertical asymptote, solve the bottom for 0. It'll give you the vertical asymptote. Okay? Let's quickly do horizontal asymptotes before I get into what this unit's really about. So horizontal asymptotes look like this. It's like if you had some line that the function never touches. It wants to, but it never does. It says they may also be horizontal. To find them, we need to check if the function values of y has limits as x goes to infinity. So remember from the previous unit, we need just to check if x goes to infinity. Let me show you how simple that is. This is your rule if you forget it. Describe what happens to this as x goes to infinity. In other words, find any horizontal asymptotes. So take our function and do limit as x approaches infinity. Just substitute infinity in, see what you get, right? This is the big part. You take your function, just put the limit as x approaches infinity. Let's substitute infinity in. You would have infinity minus 2, which is still infinity. And you would square infinity, which is still infinity. So really, you still have 1 over infinity. That's 1 over a huge big number, which really is 0. So Ali got that. It's 0. Are you not sure if it's 0 or not, Ali? You're good now. Okay. If you take 1 divided by a million or a billion, you get 0. This is the big idea here. Remember from last unit we did that, so I'm not going to talk about that more. All I'll say is that this number underneath here is huge. And so when we divide by it, we get 0. So the solution here is as x goes to infinity, the function approaches 0. What that means is there is a horizontal asymptote at y equals 0. Remember, you're solving for a value for the function, which is, it is y. F of x is y. So that's how you do these. I'll show you one more example of this before I move on, just so you're confident. Let's just say, for example, the question was, it wanted you to find any horizontal asymptotes of this particular function. Let's just say it gave you the function 2x squared plus x minus 1 over x squared minus 5x. And you should be okay with this, by the way. This is the same as saying y equals. But if we wanted to say, what are the horizontal asymptotes? All you need to do, let me give you your cheat sheet. If you want horizontal asymptotes, get the limit as x approaches infinity of your function. That's all you need to do. So we have our function. It's the black part. So get the limit as x approaches infinity. Some of you messed this up on the test. Let's try not to mess it up now again. What do we do in this case? If it goes to infinity, we divide everything by the largest power in the denominator, which is x squared. That should be pretty simple. Get the limit as x approaches infinity. What's 2 divided by x squared? It's 2. Always happens to you. 2 plus 1 over x minus 1 over x squared over 1 minus 5 over x. If you have to, take every single one and put it over x squared, right? That's the first one, 2. And then do it for the next one. X over x squared. What's that? Well, it cancels the x, cancels one of these, it must be 1 over x, and so on. All of these, if you remember, these are limits. So these go to 0. Dividing by infinity, dividing by infinity, dividing by infinity. What you're left with is 2 over 1, or 2. So the whole point of the question, it means that there's a horizontal asymptote at y equals 2. And remember that y is our function value, not dne. Yeah, it does exist. It's 2. Yeah. All good? So again, that's a review. That's not really the point of this unit, but in case those questions come up, I wanted you to be prepared. Let's get more into the meat of this unit. The domain and range, I'll give you a little gift here. I'm gonna skip it. You're welcome. Students hate that, and it's actually not that important for this unit. The rest of the practice here is just that practice. I'm just going to give you a review of what you would do if you do these practice problems. And I'll put the full solutions online, so don't worry. If you're asked for vertical asymptotes, what do? You set the bottom to 0 and solve for x. That's all you do. That'll give you vertical asymptote, okay? The next question, does the function have any horizontal asymptotes? Well, we just finished talking about that. You just need to find the limit, if it exists, as x goes to infinity for the function. For 3, any x and y intercepts, I already talked about that. If you want the x-intercept, you set y to 0, solve for x. If you want the y-intercept, you set x to 0, solve for y. That'll give you that answer, okay? Just going through it quickly today because this is all pretty much review. Find all asymptotes. That just means any vertical asymptotes, any horizontal asymptotes. The next one you can skip because it relates to domain and range. For the next one, once again, what are the restricted values of the domain? It's just another word of saying, another way of saying which value on bottom would make this explode. So set the bottom to 0. It means that x, in this case, would be -3. So the answer, you just need to say x cannot be -3. Or x cannot be -3. We've done that before. Don't worry too much about that. I'm not going to ask you many questions on it, honestly. I'm not going to use up my one special multiple choice on this stuff. I've only got one chance. I want to give you something good. The rest, same story, same basic idea. Now I want to get into what I would call the meat of this topic and the critical points that I talked about before. There are 3 main things you need to take away from this unit. First is intercepts. That's easy. Critical values, or critical points, are where the slope is 0. And so that's a maximum or a minimum point. So whenever we talk about critical values, this is what I'm talking about. All right? They occur when the first derivative is equal to 0. All right? So, in other words, if the first derivative is equal to 0, that means the slope is equal to 0, because the slope is the derivative. So to draw a little picture, if we had a little graph that looked like this, the maximum and minimum points would be here and here. What are the slopes at those points? Well, if we were to draw a tangent line, we would see that the slope here is 0. If we were to draw a tangent line here, that would be the slope is 0. So when we find our method, when we look at the procedure for doing this, the steps should make sense. Find the first derivative and then set it to 0. That'll say, where is the slope 0? If you know those points, you can figure out if they're a maximum or a minimum. So I'll just make a note. We're going to look at this. And then you substitute those in. I'll talk about that in a second. But if I follow this QR code here or go to this website, which you can do yourself, I'm talking about this over here, you can follow that. It brings up this website. All right, and I just want to talk about it for a second. I don't want to go too deep into it, I just want to do the basics. So when we look at this function, you should be able to notice that there are maximums and minimums for this function. What I mean by that is that at this point here, when x equals 2, we have a minimum. At this point here, I don't know where the x value is, but it's a maximum. And at this point here, it looks like when x equals 3, there's another minimum. Okay, hopefully that's clear. It's a high value and a low value, just like we had for sine and cosine. The important thing to know, though, is what's happening to the slope at those points. Like, what's the slope here? What's the slope here? And what's the slope here? Those are the questions you need to be asking. So let's explore this by looking at this little dot. Let me bring up the tangent line. Is the slope at this point here with this dot, is it positive, negative, or 0? And I'll just make a note here. You can always just look at this. This will tell you the exact slope, but we only care about the sign. Okay? You want to know if it's plus or minus. So the slope right now, is it plus or minus? Minus. Yes. Thank you, Mohammed. The slope as we move through this, the slope at this point, anywhere on this line here between the max and minimum, what's the value, plus or minus? Positive. So Abdelgader, I think you meant to say plus, just hit that shift. Yeah, so anywhere before this minimum, we can actually say is going to have a slope that's negative, less than 0, okay? Anywhere between the minimum and the maximum, we can say, let me try to draw this, anywhere between these 2 points, no matter where I put it, I've shifted this by accident, it's going to be a positive. Anywhere after, so let's look at this line, see how the tangent line is all pointing down no matter where I go? That means that between this maximum and minimum, it's going to be a minus. And then after the minimum, look at that. It's going to be a positive. Okay, no matter where I move that tangent line, it's positive, 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 negative, 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 positive, 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 negative, negative, negative. What is the slope at the maximum and the minimum point? Let's look at the minimum. Ooh, perfectly flat. It's not negative. It's not positive. It's 0. So the slope at that point is going to be 0. In fact, the slope at any minimum is going to be 0. The slope at any maximum, let's just double check it. Bring it up here, the slope at this maximum point, also 0. So maximum and minimum points, also known as critical values. At your critical points, also known as maximum and minimum. I'll make this clear more later. Maximum, minimum, first derivative is going to be equal to 0. That's why we're solving for it. It tells us where the slope is 0. And why I've drawn these big negative, plus, that's the slope between the maximum and minimum. And if we know that, we can actually work backwards and figure all this out. So if I lost you there, hopefully I'll get you back when we do this stuff. It says, example 1, identify the critical points of the function. And let me make a note here. We want to find where the derivative is 0. That's the big idea. Critical points is another word, another way of saying, in this course anyway, where it's maximum and minimum. Okay, Ibrahim, nice to see you here. Identify the critical points. So first things first. I have this method is here. Find the first derivative. What is the first derivative? Should be very easy. 3x squared minus 6x. Okay? 3x squared minus 6x. That step is done. Boop, boom. Now it says find all x where the first derivative is 0. So set it equal to 0, just like the intercepts. Factor this side. You should see 3x. Let's just double check that. 3 times x is x squared, yes. 3x times negative 2 is negative 6x, okay. I factored it properly. And now solve that. Well, 3x equals 0, which means, I'm just looking at this and this. 3x equals 0, that means x equals 0. And what about the next one? Split these up a little bit. If x minus 2 is 0, you just change the sign, x must equal 2. Excellent. Now, let me be clear, these are not the intercepts. These are the x values that tell us when the slope is 0. So Mohammed, you said you're kind of confused about the x. Can you tell me which point exactly? 3x, yes. You're talking about here? Yeah, Exactly. 3x equals 0. If I divide both sides by 3, 0 divided by 3 is still 0. That's what I did. Okay, so I've got some values here. Just in case I need them later, let's put them in a table. So when x is 0 and when x is 2, I'm going to put them back into the original function just to know what the values would be. So if I put a 0 in, I can see it's going to be 0. You can try that yourself. If I put a 2 into this, 2 cubed minus 3 times 2 squared is a negative 4. All right? So I have either a maximum or a minimum at 0, 0. And I have a maximum or a minimum at 2 and negative 4. So let's just write down, we have critical points at 0, 0 and 2, negative 4. Okay? So this is how this works. I'm going to go one step further, and I'm going to try and figure out if they're maximum or minimum. And that takes a little bit more work, but it all relates to what I showed you on that activity. So we're going to go down and then come back up. Increasing and decreasing functions. So it says in the graph here, or graphs in general, the graph is decreasing as it's, I find this explanation confusing, so I'm not going to read it. I'm just going to get to the point. A function is increasing. When is it increasing? It's increasing if f prime is greater than 0. Or in other words, when f prime is plus, which is exactly what I said earlier. Function is decreasing if f prime is less than 0, or if f prime is negative. Let me clarify this even more. A function is increasing or getting bigger if the slope is positive, and a function is decreasing if the slope is negative. So this is going to get more confusing before it gets better, but I'm going to make sure there's lots of examples done. Okay? If the function is increasing if the slope is positive. Look at this. Just watch this again. Follow my dot here. In this section here, the slope is negative. So just think of this as like a ball rolling down a hill. If the slope's negative, the ball is going down, it's decreasing. When the slope becomes positive, the ball is going up the hill now, or the car is driving up the hill. It's increasing, it's getting bigger. When the slope is negative, it's getting smaller. When the slope is positive, it's getting bigger. Positive means increasing, negative means decreasing. That's what it's trying to tell you. Let me show you what it means for math. I'm going to draw a little number line here. Actually, before I do that, I want to just talk about the first derivative test. I know this is a lot to take in at once, but I will do enough examples so it'll get clear. First derivative test, also known as the FDT. To determine if a critical point is a minimum or a maximum or a minimum, we need to check if it changes from decreasing to increasing or increasing to decreasing. In other words, if we have a minus turns into a plus, it's going to be a minimum. And if we have a plus turning into a minus, it's going to be a maximum. I know this is a lot to take in. You can always watch the video again, but I want to make something clear here. If it goes from a negative slope to a positive slope, think of it as a minimum point. If it goes from a positive to a minus, it's a maximum. Let me make this clear with our example up here. Again, it'll get more difficult before it gets better. Let's take a short breather. I'll explain it as if I never talked this time. I'm going to do many examples, Ibrahim. Don't worry. So let's say I finished here. All right, we got this answer. We got our critical points. I want to know if they're maximum or minimum. I want to know if they're maximum or minimum. It's called classifying. Now, yeah, Abdel, you said that it's a minimum. Sorry, there's a maximum, Abdelgader, there's a maximum and a minimum, and let me show you why. Put your numbers on a number line, 0 and 2. One of them may be a max or a min, one of them might be a max or a min, we don't know which yet. I need to test in between. So my first derivative, I want to know what the sign of the first derivative is before the 0, in between the 0 and 2, and after the 2. So let me start here. Take any number between 0 and 2. And what I'm going to look at is over here. 1, for example. So yeah, let me move this over so that I have more space. Just say I'm going to take this, put a 1 into it. 3 times a 1, and then 1 minus 2. All I'm going to do is it a positive or a negative? Well, this is a positive. 1 minus 2 gives a negative. So at the end of the day, I have a minus, yeah? Whatever number I put in, you can do that for any number between 0 and 2. 1 is the easiest. It'll give us a minus, which means the slope between those 2 points is a minus, which would look like this. The graph looks like that. Let's try it again, just in case you didn't catch that. Let's try after 2. So we'll try a number, I don't know, 5. So 3 times 5, 5 minus 2. 3 and 5 gives a plus. 5 minus 2 gives a plus. A plus and a plus gives a plus if you multiply them. So after 2, the slope must be positive or the graph is increasing. Again, you should be able to do these very quickly, so I'm not going to write the workings out for all of it. What about the before 0? Let's say try negative 1. Again, I'm trying into the first derivative. 3 times a negative 1, a negative 1 minus 2. This gives a negative, this gives a negative and a negative give a plus. So anything before 0, the slope must be positive. Okay, so first time around, I know this is a lot to take in, but the rules don't change. I'm just showing it to you. Let me get to the point. If you're going, yeah, we substitute numbers, any number between 0 and 2. So I use the number 1. Does it give a plus or a minus? I give the number 5. Does it give a plus or a minus? I took a negative 1, plus or a minus. And now, look what's going to happen. If these are slopes, right? This is slope. So if it's a positive slope, you know, positive slope in this region, negative slope in this region, I must have a maximum. Look at what that looks like. That's a maximum shape. If it goes from positive to negative, it has to be 0 at some point. It changed to, it must be a maximum. Same story here. It goes from negative to positive. That's a minimum. And so what that means is that the x equals 0 value is a maximum. The 2 and negative 4 value is a minimum. I'm going to show you that on Desmos in a second, but look at how all this connects. A lot of things going on here, but it all is saying the same thing. If the slope is positive, it means that the function's increasing. Or more importantly, if it goes from a negative to a positive, it's a minimum. Negative to a positive becomes a minimum. If it's positive to negative, we're talking about slope, maximum. Let me show you what it looks like on Desmos so that you can make one more connection. At some point, it'll click together in your head, but for some students, it takes longer than others. So let me type out this function so you can see what I'm talking about. F of x equals x cubed minus 3x squared. Okay, this is what this function looks like. All right, this is what this function looks like. Let's see if our numbers are what we say they are. This function has a maximum at 0, 0. It has a minimum at 2 and negative 4. Looks good so far. Let's try and mark it up. At between 0 and 2, it says it should be a negative slope. That's a negative slope. It says after 2, it should be a positive slope. That's a positive slope. So in between, you can't possibly go from a minus to a plus without crossing 0. So there's a 0 slope right here, and it's a minimum. We can look at the graph and confirm that it must be a minimum. Okay, let's look at this. Before 0, to the left of 0, the slope is positive. To the left of 0, this slope definitely looks positive. And so if we look at the point that it changes from a positive to a negative, it's definitely a maximum. which is what this says, maximum and minimum, maximum and minimum. I know I've just scribbled all over this, but can you just tell me on a scale of 1 to 10 how much this makes sense to you so that I can focus on things? 9 and 10. Superstars. 5, okay, you got some regular mere mortals here. We can't all be Raiden, demigod of the nether realm. Okay, so let's see here. I guess it's not nether realm, earth realm. Thunder god of the earth realm. Does anyone know what I'm talking about? Okay, well, anyway, our question's done. Let me try and recap. All the critical points. Where is it a maximum and a minimum? Well, we found that. It's right here. And then we classified them. Is it a max or a min? And we found that out. Let's do more examples. By the way, if the sign does not change, it's not a maximum or a minimum. Let's not worry about that for now. Let's pick apart this graph. Consider the function. You get it all on one page here. Let's see. Let's answer these questions. At B, so it says, at the point B, I'm looking at this, we have what? Is it a maximum or a minimum? Well, that's an easy question. That's a maximum for sure. And just as a reminder, the slope is the first derivative. Let's all keep that in mind. At D, we have a minimum from A to B. So that's this, from A to B. Let me make it more clear. From A to B, the graph is increasing. So in the chat, I saw a positive. Yes, you're right. It means the first derivative is positive, or in other words, the first derivative is greater than 0. You'll see both types, positive slope, okay? That just means it's a positive section. Excellent. From B to D, talking about this, from this B to D, the graph is decreasing. Exactly. So I'm seeing that in the graph. That's excellent. I'm seeing that in the chat. That's excellent. That means the slope in this case, less than 0, also known as negative. Okay, slope. From D to E, the graph is definitely increasing. For the same reason as before, it's got a positive slope, yeah? It's got to be, no matter where you take that tangent line, it's going to be positive. Even right down here, it's positive, just less positive. At A, the slope is positive. Definitely positive. At B, where's B? Ooh, slope is 0. Yeah, Mohammed, you weren't so sure about that, but you got it right. At B, the slope is 0 because it's a maximum. It means f prime is equal to 0. It's a maximum point there. They're all related concepts. Let's see, what else do we have? At C, the slope is, a lot of students get C wrong. I've never been able to understand it, but C is a tricky one. At C, the slope is not 0, slope is negative. At D, the slope is, let's check the tangent line at D. It's changing from a minus to a plus. Slope is 0 at a minimum. Okay, so we're making sense of the curves. We're making sense of curved sketches, right? This is a sketch. If you're not sure about this, by the way, notice that it looks like this. A horizontal line has a slope of 0. And finally, for E, at E, the slope is, well, it's going up like that. We draw a tangent line, so it should be positive. Okay, so we've got our basics here. If you're not sure what's going on, just rewatch the video because I don't have a lot of time to go back. Hopefully it's clear. All about slopes. So let's do an example. In fact, let's do 3 more examples, and hopefully what I'm doing will start to make sense to you. Identify the critical values of the function, and then determine if it's increasing or decreasing. All right. The only change I'll make is that I've crossed out this because that was a really bad example. It made it more complicated. just use my slightly altered version, okay? Let's follow the steps. I know I'm going to want a table of values, so I'm going to just draw that in first. And let's get started. First derivative. Let me be clear here. I'm going to say my critical points is the step that I'm doing, which I set y prime equal to 0. Y prime, f prime, same. First derivative is 3x squared plus 6x minus 9. Hopefully you can all see that clearly. I'm going to set it to 0, and I'm going to solve for x. But I can't solve for x until this thing's factored out. So let's take out a 3. We have x squared plus 2x minus 3. Factor that. That should be a nice, easy one. Two numbers that multiply to make negative 3 and add to make positive 2. It's got to be 3 and negative 2. If you're not sure, check it in your calculator, do what you need to do. Wait a second, negative 1. I almost ate my words there. Maybe it's not so easy. Thanks, Abdulgader. Now, set this to 0, set this to 0. What you'll see is that x equals negative 3 and x equals 1. I'm going to put those in the table. Those are my critical points. In fact, I'm going to go ahead and just put them right into here and see what I get. To save time, I'll tell you what I get, but again, I'm taking these and I'm going to put it right into here to see what the y values are at those points. And it turns out that I get 28 and negative 4. Now, what are those points? Those are where we should have a maximum or a minimum. And I'm going to test to see if they are maximum and minimums. I'm going to do the first derivative test. Set up the number line. What will happen if we didn't get it? So, Mohammed, what do you mean by didn't get it? Didn't get what? If you didn't get the y values? But by get, do you mean the coordinates, or do you mean you don't understand the concept? What do you mean when you say you didn't get it? Well, the whole point of the question is to find them. So if you didn't get them in the end, you just didn't solve the question, which means you don't have the answer to the question. So the whole idea is that the critical values are where x equals 0. Where the function, the slope equals 0. You have to solve for those x values. Once you find these, if you stop here, you're not done, because the whole point of this is that at some point later, we're going to be sketching these by hand. And in order to sketch them by hand, you have to know if it's a maximum or a minimum, or else the function will look totally different. So let's just keep doing the examples and classifying, and hopefully it'll become more and more clear. So what I'm going to do, this is a number line, just like a regular number line, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Negative 3 is the small one, and 1 is the big one. Okay, maybe I'll move this over just so it's more clear. And I need to take any points, and put them into this. I just need to go anything less than negative 3, anything between negative 3 and 1, and anything bigger than 1. So 0 is a very logical thing to take. So I'm not going to keep these workings here. Actually, I will keep them here, just so that some of you, if you're lost, you can follow. But I'm going to take 0. So just test 0. That means we have 3, 0 plus 3, 0 minus 1. That's a positive and a negative. That gives a negative. So I have a negative value here. Okay? I'm not going to keep those workings there because I don't want you to think that you need to write them all out. And you can you can take any value. Okay? Just gives our minus. Let's try another one. What about anything bigger than 1? Well, let's just take 2. So put 2 in for x. That's a positive, that's a positive. So in the end, I have a positive. That region's positive. I'll do one more. Oh, anything below this, let's just say negative 5, that's perfectly fine. Or negative 10 is sometimes easier. Negative 10 plus 3. negative 10 minus 1. Remember, this is all this. Just putting them all in. That gives us a negative and a negative. Wait a second. Something feels weird. This is a negative. Yeah, negative and a negative. What am I doing? What am I doing wrong? Why is my brain not working? Negative. A negative makes plus. Yeah, okay. Who was right? I was off in space there for a second. Okay, so just so I'm clear, this one gave this, this one gave this, this one gave this. I'm going to erase those, but just so we're all clear where these signs are coming from. Chill. It's been a busy week, okay? It's only Monday and I'm already burnt down to a little tiny nub. Marking for 5 hours yesterday, moving houses, preparing a final exam, preparing these notes. It's a lot. Taking care of a 2-year-old. There's lots to do. Don't judge me. Okay, what was the point? The point was to label them as maximum or minimum. So let's look at this. Let's label it. For this one to this one, we're going from positive to minus. That means positive slope, negative slope. This is a maximum, which means that I'm going to cheat here because I didn't give myself enough space, which is just the story of my life. I'm going to call this one a maximum. The next one is probably a minimum, but let me double check. I see your question there, Ibrahim. This is negative to positive. Definitely this is a minimum. So this is a minimum. So Ibrahim, you said, sir, we choose any points depending on negative 3 and 1. That's exactly right. You could choose, for example, in this region, you could choose negative 2, negative 1, 0, or anything in between. Just something between negative 3 and 1. All we care about is the sign. Let's make this clear, okay? The first derivative test, we don't care about the number, we care about the sign, plus or minus. So you say, when I take any point, I can use the first equation. No, because the whole point of the first derivative test, this first derivative test, you're testing the first derivative. You cannot check the original equation or else we wouldn't need the derivative in the first place. The first function gives you just values on the graph. The first derivative gives you the slope of the graph. And it's the slope that tells us if it's plus, if it's minus, if it goes from plus to minus, if it goes from negative to positive. Those are the things that tell us about maximum and minimum. So in short, no, you can't use the first equation for your maximum and minimum values. Any other questions before I show you what the graph looks like? I'll take that as an and. So the question says, determine where the graph is increasing and decreasing. That's what we're saying here. On the number line, this is increasing, this is decreasing, and this is increasing. That's what those positive and minus mean. Let's look at the graph so that we can compare, and you can start making more connections and see if you can make sense of this. So let me reset this graph. It is x cubed plus 3x squared minus 9x plus 1. That looks about right. It looks like this. All right. So let me get it the right size. All right. I'm going to compare this to what I have on the left. So I'm saying that there should be a maximum at negative 3 and 28. And there is. Okay, good. And there should be a minimum at 1 and negative 4. And there is. Okay? Let me try and make the number line more clear. If I look at this number line, this number line here relates to this point and this point. What it's saying when I talk about slopes, it's saying that to the left of negative 3, to the left of this point, it's always a positive slope. So this entire region, no matter where I go, is a positive slope. That's what this positive means, okay? Anything between -3 and 1, anything between these two lines is a negative slope. That should make sense because look, negative, 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 negative. All of them are negative. That's why I do my number line. I don't have to graph it to know that it's negative. I can use the first derivative test. And then after after 1, it says it's a positive slope here, which definitely this is all positive slope. In between the sign changes, which I'll put in purple, if it goes from a positive to a negative, it must go to 0. It must be flat at some point. That's our maximum. And if it goes from negative to a positive, there must be a point where it's 0. The slope can't magically jump from negative to positive without going through 0. And so that's our minimum point. So hopefully this is making some sort of sense. These are fundamental, and this will actually help you in the next math course as well. A lot of math courses or a lot of math teachers won't even show the graph. But to me, the graph is the most important part. Like, I can't make sense of this unless I see the graph. And as soon as I see the graph, then I can make sense of my work, not the other way around. So once you're doing this, it'll slowly piece together. It should be very logical. If it doesn't make sense to you, do some practice, come watch the video again, do some practice, and so on. Come back and forth. All right, let's see. This question, 3x squared and 2x, we already did this. Example 3 was example 1. So I'm actually going to skip it. We did it earlier. I'll do example 4. And let me see, I think I made a change to example 4. Yeah, I wanted to make it an easier function because this was a really stupid function to give. Let's say 3 over 4 x power 4 plus 4x cubed minus 45x squared minus 4. This is our actual function. And what it's asking is for us to find the maximum and the minimum points, also known as the critical points or the critical values, mean the same thing, on the graph of the function. Okay, so once again, I'm going to make my table of values because I know I'm going to need it. And I'll go through my process again. So I need to get the first derivative, yeah? First derivative will give us our critical values. I'll just write CV, critical values. The derivative, which hopefully you can check this yourself, what's 3 over 4 times 4? It's 6 x cubed plus 12x squared minus 90x. And the derivative of negative 4 is 0. So this is our first derivative. I'm going to solve this. I've got a 3. What's 3? Oh, yes. Sorry, I have a typo, but it's not there. It's here. The original function is supposed to be 3 over 2. That was why I thought it was a 6. So I made a mistake, but make that change, okay? That was my bad. But if we change it to, if I put in 3 over 4, it'll change it completely. My bad. I'm only human. We're all only human, hopefully, except for you weird computer robot people out there. All right, let's solve it. Make it equal to 0. Take out any common factors. You'll see that you can actually do better than the 3x. The 3 was a mistake. So let me be clear, the 3 is not correct. If you're writing 3x cubed, it's because I used the wrong function. This is actually pull out a 6 and an x. You get x squared plus 2x minus 15. Yeah, you can do it with the first obligata, but I think you might get more difficult factors later. So I don't recommend going with that. And I'm glad you forgive me, Abdo. Very, very sweet of you. Okay, let's factor this. 2 and 15. Let's see. That would be a 5 and a 3. 5 and a negative 3. You can do it on your calculator if you want to. I showed you how to do that earlier. And now we just solve 6x equals 0, x plus 5 equals 0, x minus 3 equals 0. That gives us critical values of x equals 0, x equals -5, and x equals 3. If you stop here, well, you shouldn't stop there because we don't know if they're maximum or minimum yet. So I'm going to put those in. We can get a good idea by putting them back in. I'm not going to put them into this equation, although I could, because they're a little, okay, let's put it in. -4. I might as well, just to make the question complete. That would be if I put a 0 in. Let's put a -5 in. You can either do this with me or take a short break. I'm just going to be putting in these numbers. 3 minus 45, -5 squared, minus 4. This gives -691.5. Don't freak out. It's okay to be small. Let's see. And -179.5. In case we need them, that's what they would be. You probably don't need them most of the time, but it's important to at least keep a note of it. Let's do the first derivative test. We're going to tell the person asking, which is me in this case, are they maximum or minimum? And we're going to do the first derivative to prove it. So let's put our numbers on the number line. 0 in the middle, 3 over here somewhere, -5 over there somewhere. And the whole point is we want to know if we have positive or minus in these 4 regions, because that'll tell us if it's max or min. So we can tell max or min according to the highest and the lowest y value. You could, yes. Once you get your critical points from the first derivative, you can tell it. There's usually multiple ways of getting it. The problem is you'll get a relative. Well, there's no problem. To be clear, okay, one second, I got another question here. Do we put them in the original equation or to get what? All right, let me answer the 2 things. Ali, yes, you can usually tell if it's max or a minimum. The problem is for more complicated functions, sometimes it looks like a minimum, but it's actually just like a curve in the graph. And it doesn't actually become a minimum. It just goes up, flattens out, and goes up again. And so we can't actually tell what's going on unless we check the slope. Those are special cases, but they do happen. So I would say 90% of the time, the table can tell you. The other 10%, the table is going to lead you wrong. So we do the first derivative because it's more specific and it helps us more. But you can definitely check your answer with the table. As for Muhammad, do we put them in the original equation? No. And the reason I say this, remember, this is the first derivative test. Everything about this is with the first derivative. Don't go back and use the function. Use the first derivative because that is our test. We're putting values into the first derivative to see what the slope of the graph is, if it's positive or minus. So in short, Ali, the answer to your question is yes, you can use a table, but it won't always work. And Muhammad, the answer to your question is you use the first derivative equation. Let's check this. If I put in any number between 0 and 3, putting it into this is the easiest way to do it right here. If I put a 1 into that, I get a positive, positive, and a negative. That would give a negative overall. So I'm just going to put a negative here. You can put any numbers in, and you'll get that. I'm going to take that first derivative and try something bigger than 3. Let's say 4 or 10. Let's say 10. 6 times 10, and then 10 plus 5, and then 10 minus 3, for example, would give a positive and a positive, so that must be positive overall. Again, these are values for the slope. It's if the first derivative is positive or negative. Abdul Ghadir, you shouldn't be getting all minuses, so something weird is going on here. Let me check between 0 and 5. I'll try a -1. So 6 and a -1, -1 and a 5. -1 minus 3. That would give a negative, a positive, and a negative. Two negatives make a positive. So that's a positive. Finally, something less than 5. So I'll try -10. 6 and -10. -10 and 5. -10 minus 3. Let's see, that's a negative, and a negative. Two negatives make a positive, but it keeps that negative there, so overall I have a negative. So that's a little tricky, I'm not going to lie. To do the tests is not always super, super easy, but the more you practice this, the better you'll get at it. And again, I'm just putting any numbers in. So Mohammed's, you got minus, plus, minus, plus. That's exactly what I got. Abdelgader, I'm not sure how you got the 3 minuses, but maybe you had a mistake between the -5 and the 0. So whatever number you chose, maybe try that again, double check the signs. And of course, you can put the number into your calculator. I'm just doing it by hand. But you can put in the numbers. You just calculate it out and steal the sign from the answer. Either way, you should get this. So let's label these. Minus to a positive, that's a minimum for sure. Plus to a minus, that's a maximum. Minus to plus, that's a minimum. Oh, you did it with 6x. So this is our final answer, really. At 0, we should have a 0, 4, we should have a max. At -5, we should have a minimum. And this should be a minimum as well. So I'm going to clear my work up a little bit. I know you can't do this, but I'm trying to do this so that when you look at it later, it's more clear. I've classified it. So the answer is finished. Let me double check. Find all maximum minimum points on the graph. I've done that. You had to do all the steps to get the maximum and the minimum points, okay? Can I clarify anything before I make the actual graph on Desmos? The steps, once you get used to it, the steps are definitely new. The steps themselves are actually not difficult, but to remember all the steps and follow them correctly is more complicated than usual. I've done it both ways in the past. I've showed every single step, and I've showed the smaller way, and eventually it just clicks. But you got to do enough of these for it to click, as usual. Okay, so let's compare our graph to Desmos. Now, I always do this so that you can make some sense of it. Do it yourself on the test, if you get this question. Let's see. Let's put in this graph, see what it looks like. 3 over 2, x power 4, plus 4, x power 2, 3, minus 45, x power 2, minus 4. So this is our graph. She's a beauty. Okay, let's see what I have. I should have, zoom Y. Let's see, I should have a minimum at 0 and 4, and I do. I should have a minimum, sorry, a maximum. Should have a minimum at -5. I don't have my whole graph here. Aha, almost lost that. Okay. Those are my important points. You'll see they match what we said. 0 and 4, maximum. 0 and 4, maximum. -5, 691.5. 3, 179.5. Okay, our derivative test said that it should be between -5 and 0, it should have a positive slope. And it does. It says earlier than -5, it should have a negative slope, which it does. Between 0 and 3, it should be negative, which it is. And after 3, it should be positive, which it is. And by knowing that, I'll just draw over this again. Negative to a positive means we have a minimum. Positive to a negative means we have a maximum. And negative to a positive means we have a minimum. So I know I'm scribbling on this, but the whole point is just check the slopes. If you have a sign change, it's a minimum or a maximum. Negative to a positive, minimum. Just look at the shape. Positive to a negative, maximum. Again, just look at the shape. And it should be enough. By shape, I mean look at the shapes that you draw based on the signs. Okay, anything I can go back over before I erase all this? Okay, so there's only one more thing left to do in this unit. It's called concavity. And we've actually already been seeing it without even realizing it. Concavity is how the graph looks. Remember? It's kind of like in physics, is it accelerating or decelerating? Or in the parabolas, does it look like this? Smiley face, which in this case, it looks like that. Or does it look like this? And we have what's called positive concavity, or concave up, or negative concavity, which is concave down. And those are the only things left. So before I do concavity, let me just finish the very quick question here at the bottom of the page, and we'll do the last topic of the unit. So it says in the graph below, classify the local extrema or absolute. And what this means is, well, it says above here, it can have, a graph may have a number of maximum or minimum values. They're either called relative maximum minimum points or local, or they're called absolute. If they look like a maximum, they're definitely a maximum. If they're the biggest number, they're called the absolute. So let me show you what this means actually. A, B, C, D, E. At A, we can see clearly that it's a minimum. Is it the smallest value on the graph, or is it just a minimum? Well, I can see that this is actually what we call an absolute minimum. Because if we look at A, there's nothing below this. The A value, it's definitely a minimum. It's the smallest possible graph, smallest possible point on the graph. For C, we can see it's definitely a minimum. I hope you can see that. Wait, B. Sorry, B. We can see that B, if we zoom right in on B, you can see it's a maximum. You know, it's definitely got a maximum shape to it. So we can say that it's a maximum, but is it the biggest number on the graph, or is it just a maximum? Is it the biggest number? No, there's plenty of numbers bigger. Everything above B, there's tons of graph up here. So we say it's a relative maximum. Just a max. It's not the maxiest max, it's just a max. But relative to the other numbers, it's got its own little maximum going on. C. C is a minimum, for sure. But like Mohammed just said, it's a relative minimum. And it's a relative because it's a minimum for sure. It's got that dip, but it's not the minimumist minimum. It's not the smallest minimum. D is a maximum, but in fact, it's actually only a relative maximum. And the reason for that is because this graph actually continues. So it's a maximum value, but it's not the maximum. The function gets bigger on both sides. So that's a tricky one. In fact, I would say it's very tricky. So be careful with that. It's the biggest maximum, but it's not the biggest number on the whole graph. So that's a weird one. Let's look at E. That one is a minimum. Is it the smallest minimum? Is it the most minimum? Well, E is right here. There's definitely values below E, so it's only a relative. It's definitely a minimum, but it's not the smallest point on the graph. And that's what this stuff is talking about. So if that doesn't make sense, go back through the video, try to piece this together again, and hopefully it will become more clear. So let's do the last topic, shall we? The practice is just that, it's practice. You can do it for homework, it's based on what we've done already. Sorry, my computer just freaked out there. I've put the answers here. It should be 0, 1 over 2, and -2, if you want to try that yourself. For the next question, once again, same idea, critical points, max and min. I put the solutions here, 3 and 1. You just need to tell me if they're maximum or minimum. 3 here would be a challenge, and I would not ask it. In fact, I'm never going to ask it in this course. It's a question that'll come up in the next course, so you can worry about that in the next course. Let's do one last topic, shall we? And I've already kind of foreshadowed it. It's called concavity, and it's all related to the second derivative. Let me just get some things out of the way before I show anything else. We say a curve is concave down if it opens downward. So it looks like this or some part of this, okay? We say a curve is concave up if the curves open upward. That means it looks like this or some part of this. It's talking about tangent lines here. It's saying that if the second derivative is negative and the curve is concave down, it looks like this over here. And it says if you try to draw a tangent, the curve is going to be below the tangent. I don't find that the most helpful definition, but some students like it. If we look at the final type of concavity, concave up, the second derivative is above 0, also known as the second derivative is positive, then we have concave up. That means if you try to draw a tangent, the curve is going to be above the tangent. Once again, I don't find that to be super helpful, but that's the idea. Let me give you a little cheat sheet. Actually, I'll look at this graph one more time, and then I'll give you the cheat sheet. Remember this, old friend? Forget about second derivative. Let's look at first derivative. I want you to look at this right here. We're going to play a little game, okay? You tell me when that number changes from positive to negative. Okay, right now it's positive. You tell me to stop when it goes to minus. Oh, someone said stop. Somewhere around here. Let me make a note of this. Something's important here. Something important happening. Let's keep going. Tell me again to stop when it becomes 0. Oh, okay, I saw another stop. Obviously, I know why I'm doing this, but something special about this point. Let me try to summarize. The second derivative here has to do with concavity. Or in other words, it has to do with what's called inflection points. What we've done is we've identified 2 inflection points. Let me try to make it as clear as I can. You told me to stop right here. You told me to stop somewhere around here. What's happening is it's twisting. It's going from what's called positive concavity to negative. Look at this. This graph here, if we look at just this section, it's got a positive concavity. It looks like this. In that region, it looks like a part of a smiley face curve. In the middle here, it has a negative concavity. It looks like concave, a different kind of concave. And then on the right side, it looks like this again. So it's almost like 3 graphs stuck together. And the big idea here is on the left side of this, this is called concave up, because it looks like this. In other words, the second derivative was positive. This area looks like concave down, which looks like, well, as we see, looks like this. Second derivative is negative. And this area on the right side, once again, concave up, because it looks like this. Second derivative is positive once again. So long story short, our function gives us intercepts. The first derivative gives us maximum minimum. The second derivative gives us inflection points. These are called inflection points. Hopefully you can see visually what they mean. It's where the graph twists. It goes from a smiley face shape to a sad face shape, or vice versa. Okay? Those are the big points that I'm trying to make here. So let's go back to our story. I'll give you a little cheat sheet. We have 4 possibilities for what parts of a graph can look like. We can have second derivative, in this case, is positive. Negative. We can have second derivative, in this part is negative. That's because it looks like this. Both of those are parts of that curve. You can have second derivative positive, second derivative positive. Okay? Because together they look like this. What about the slopes? What's the slope of this section? Right, these are 4 different cases here. What's the slope of this top left? Is it positive or negative? Well, in all cases it's positive. So this side, the slope to me looks like it's negative, it's going down. So the slope here is negative. Here, the slope is negative. Here, the slope is positive. And again, you don't need to know all this off the top of your head. I'm writing this so you can figure it out later. I'm going to rearrange this so I don't confuse anybody. This is what I would call your, your cheat sheet, your reference sheet. If I ask you this kind of stuff later, you can come back to this. There's only 4 possibilities. It's either curved this way with different slopes or curved this way with different slopes. So let's see what these questions look like, okay? Because I've been talking a lot. It's not my style, but it's going to be important later. So hopefully this makes sense up here. This is just a reference for you. Second derivative test. Ooh, we're going to have a second derivative test. Or it must be having to do with the second derivative. Let me tell you what it is. We can use concavity to determine if a critical point is a maximum or a minimum. Curve is concave down at a maximum point, concave up at a minimum point. We can check the second derivative, and it will tell us if it's a relative maximum or minimum. Let's get to the juicy stuff, okay? I'll write out what this means in English. You can test the critical point using the second derivative. If you get less than 0, it's concave down, which will be a max. If you get greater than 0, it's concave up, and that'll be a minimum. Finally, I know this is a lot of talking, but I want to get this out there. At an inflection point, the points which I just talked about, the points at which the curve changes from concave up to concave down, or from concave down to concave up, is known as points of inflection. So in order to follow this process, this is what we're going to do. Same process as always. Same process as the first derivative test. You're going to get the derivative. You're going to set it to 0. You're going to solve for x. And you're going to check the signs. Let's do that. Because I think it's more important to do the examples. Let's pick apart the graph, and then we'll actually do the math part. So let's look at this. From I to B, see if you're still awake. From I to B, the graph is what? Concave up or concave down? Concave up. Yeah, good job. Concave up. Also, in other words, that means that the second derivative is greater than 0, also known as positive. Or you can think of it as this being part of this graph. So it looks like this, which again, second derivative positive, that's what it means. From A to I, graph is concave down. In other words, second derivative less than 0, negative. It looks like this, which means the second derivative is negative. I'm trying to give you as many ways of looking at this as possible, but hopefully it's making some sort of sense. I is, what's I? What's the name of I? That part in the middle when it changes from concave up to concave down. That inflection. The inflection point. Also known as a change point or a changing point. In this case, it went from concave down to concave up. That's what's happening there. Let me make it really clear to you. It changed from this shape to this shape. And so in the middle here, when it changes its story, it's an inflection point. Let me make this clear. Concave down, concave up. All right, I'm probably giving you more information than you need. You're probably like, I get it, I get it, I get it. But maybe in a day or so, you won't get it anymore. And you want to go back to this and say, yeah, okay, he was right. Like, I understand. So M, final question here before the actual mathy part. M is, well, what's M? This is M. Is it a relative or an absolute maximum? I guess is what it's asking about. Well, in this case, it's a relative maximum. That's because this function will continue up and get bigger. What's little m? It's definitely a minimum. Is it a relative or an absolute minimum? It's a relative because it's a low number, but if we follow this, it would keep getting smaller than that. So it actually is a minimum, but only a relative minimum. Sir, my mind stopped processing. It's okay. I wish that I had more time to go through this, but unfortunately, I've got to get it out today because of the length of the term. You can rewatch the video after. We'll do one more example. This will be the last example we do, which I'll just blow your mind just a little bit more, and we'll recap it on Wednesday. Because tomorrow we're going to do Unit 7. It's less thinking. It's very straightforward. Tomorrow, the topic is so straightforward. Today, not so straightforward. So let me finish this, and we'll do some review on Wednesday. And let me be clear, when we do the review, I've made the review so it'll focus on the final style questions. And so if you actually come to the review and do it with me, you should be able to get full marks on both of these questions, the one for Unit 6 and the one for Unit 7. And I'm quite confident in that. All right, I designed it so that it'll help you understand the questions you're going to get asked. All right, let's get one more question done, and I'll leave you alone, okay? How's that sound? I'll take that as a yeah, sounds okay. I don't know if you can even process that. You're just like, don't fall asleep, don't lie down too, don't get too relaxed. Some of you are probably on your bed just like, what is even, what's it, what? Anyway, I understand. Example 3. Determine the concavity and any points of inflection of the function. I'm going to add something because I'm a horrible person. Determine the critical points and the concavity and find any points of inflection. So we'll get a special question, right? All things considered. I know I'm going to want the table of values, so I'm going to make that. Let's get started. First things first, we want the critical points. Or the critical values, they mean the same thing. How do I get the critical points? I get the first derivative, set it equal to 0. Let's do that. First derivative is 3x squared minus 3. Set it to 0. I'm going to factor it because that'll make life easier. This is a difference of squares. So when you notice this, you probably already know what it is. You've probably seen it 100 times. It's x plus 1 and x minus 1. The reason I know that is the first value is the square root of this. What's the square root of x squared? X. What's the square root of 1? It's 1. So you put that in both places, and then you just put a plus and minus. So it works with all sorts of stuff. What are our x values? Solve both of those. Okay. I've got 1 and negative 1. So I'm going to make those blue because I'm fancy. And this is my negative 1 and 1. And if you put those back into the original function, which I'll make sure you know, the reason I'm allowed to do that in the original function at this point is because I'm looking for the function values. I'm just looking for the coordinates, and that has to do with the original question. If you put those in, what you get is a 2 and a negative 2. All right, I'll just put those there. You can check it yourself, but I'm pretty sure they're right. 99% sure that they're right. Okay, what do we need to do next? Let's see if you can remember what we did in the last topic. Critical points. What do I do? Once I get them, how do I find out if they are maximum or minimum points? I have a pretty good idea. Based on this, this is probably a maximum. This is probably a minimum. But if the function was any more complicated, I wouldn't quite know. Yeah, Zara says substitution. There's a specific name for it when you do the second derivative, or sorry, first derivative. And it's called the first derivative test. I'm going to do the first derivative test. That means we are trying to check when the first derivative is plus or minus. Just check our values. So we have a negative 1 and a 1. Yeah, your brain. My brain! Let's put in a 0. If we put 0 into this, just put a 0 in. You know, you can actually calculate it if you want. You put this in a calculator if you don't want to do it by hand. This is a plus, this is a minus. A plus and a minus give a minus. This is a minus area. So let's see. Anything less than negative 1. I want to check this region here. Try anything less than negative 1. It doesn't matter what you put in. Let me try a negative 10, just for funsies. This is a negative, this is a negative, that gives a plus. And let's try anything bigger than 1. Let's try 2. So that's a positive out of 2 minus 1. That's a positive. Plus, plus makes a plus. So I have a plus over here. I want to make a note here. Many students kind of get a little too confident. And they're like, well, if it's a plus here, it's a minus there. If it's plus there, it's a minus there. Plus, minus, plus, minus, plus, minus. That's not always the case. So don't get lazy and think that they are always in that pattern. It's not the case. All right. I know, Mohammed, you said your brain is dying. It's fine. I'm just going to keep going as if everyone's still alive, you know, and then you can, you know, pull yourself back as a zombie like Last of Us 2 and try again later, okay, when you watch the video. Let's see. Plus to minus, that makes a maximum. Minus the plus makes a minimum. So concave up and then down. We don't know that yet, Ali, because we haven't done the second derivative. This is just the maximum and minimum. So that means that x minus 1 is a maximum. It means x1 is a minimum. I can also label it over here. I don't care where you label it. I'm just showing you every possible place you could put it down. And you can't hear me? Can anyone else hear me? Can you hear me now? Zara, I think maybe you muted your mic, your sound. Maybe, I don't know. Can you hear me now? Did you guys have that commercial over here? Can you hear me now? Can you hear me now? That was a classic from Canada. Anyway, sorry, Zara. Everyone else can hear you, so I'm going to continue. So that means our graph looks like this. Like this. Turn the volume, maybe. I'm just going to say I don't know how to help because I don't. Zara, maybe instead of you dying, your computer is dying because it just can't take it anymore. Maybe that's what's happening. Math has that effect on people, and apparently machines. All right, let's keep going. We're almost done anyway. You can always rewatch this part. So I've labeled my maximum and minimum points. Now I need to do my inflection points. That's setting the second derivative to 0. Yeah, you just log out and log back in. I guess you can't hear me, so I don't know why I'm trying to give advice. So Ali, I think it was you that said concave up and down. We don't know that yet because we haven't done the second derivative yet. So let's do the second derivative. Second derivative is, we're taking this, second derivative of 6x. Set it equal to 0. That means that x is 0. Okay? What that means is we have an inflection point at 0. Let me put this in the table. Can you hear me now, Zara? Hopefully you can hear me. Okay, good. Inflection point at 0, if I put it into the original equation, it gives me back 0. So actually the inflection point is at 0, 0. What does the inflection point mean? It means when it changes from a positive to a negative, or sorry, a concave up to concave down. I'm just going to go ahead and write out the rest, and we'll cover more of this on Wednesday, because I know most of you are probably shutting down now. Second derivative test, what does it look like? Well, we put our inflection point in, check the signs. That'll give us the sign of the second derivative. I'll just cut to the point. If you put in any number, yeah, even my computer is probably shutting down. I'm having internet trouble too. So I'll finish this question and we'll move on, okay? Any number bigger than 0, it gives us a positive value for the second derivative. Just put it into here. Any number, put in a 1, 2, 3, 4, 5, it's a positive. Any number below 0 gives us a negative here. What that means is that in this region, it looks like this. And in this region, it looks like this. Okay, that's the big idea here. That's what we're trying to figure out. Let's see if we've solved the question. It says, determine the concavity and any points of inflection of the function. Okay, I've done the critical points, max and min. I did the inflection points, and then I have the concavity written on my graph. So just to be crystal clear, let me write out the final answer, and I'll let you all go. So we have an inflection point at 0, 0. I have concave up when x is less than 0. Concave down when x is less than 0. Concave up when x is greater than 0. Okay, so there's lots to talk about there. I wanted to go into more detail, but I don't think there's any worth right now. I'll recover anything I need to on Wednesday. But for now, those are the big concepts. That's the entire unit. Take a break, watch the video when you have some more brain power, and the next class will be matrices, much more straightforward. I promise that. Yes, so Ali, you said the first derivative gives critical points, the second derivative gives inflection points, and I actually said that earlier. I know we did a lot today, but I think I said that right at the beginning. we've covered everything. This is the big idea. Okay, just so I'm clear. First derivative gives critical points, second derivative gives inflection points. All right, I'm going to stop the recording here. See you all later.